All right, the exceptions to your transition metals. So your book gives you several different exceptions. I only want you to know 4 of the exceptions. The reason that is because if we include the ones that your book gave us, then every time you do an electron configuration with a transition metal, you're going to try to do what I'm about to show you. Okay, so only know these 4. Chromium. So let's write chromium's electron configuration as we would know it right now.
Okay.
We would do argon, mm-hmm. 3D4. This is what we expect.
That's not what happened.
So instead, what happens is we put only 1 electron in the 4s orbital and 5 in the d orbital, because if we do 5, not only have we maximized our same spin, but because it is completely half filled, it can form more bonds because we can insert an electron in each one.
Gotcha.
So this the other one that does the same thing is MO. You'll you'll notice MO is in the same group as chromium. Elements in the same group tend to act the same. So the same will happen with MO. It would be Kr 6s1 4d5 for the same reason. It's supposed to be.
S1 for
D5.
4.
So that's 2 of them, and they're the same. They do the exact same thing. The other 2 I want you to know are copper and silver. They essentially do the same thing. They only put 1 electron in the s orbital, but this time they will be completely filled in the d orbital, not half filled. So we did copper, argon, 4s2, 3d9.
So we do 2 in the S orbital?
No, that's what we'd expect.
Oh, okay, I'm sorry.
So how it actually is, again, you take 1 from the s orbital, you put it in the d orbital so that it's completely filled.
So it's 4 D6, I mean 10.
10, yes. Exact same thing for silver. It's just going to be 5s 4d. So
Okay, or
yes, those are the only 4 I want you to know.
where am I getting? Oh, yeah, because we brought it over. I'm like, why am I only getting that?
Yeah, we took one.
We brought it out. Yeah.
That's the exception.
We stole it. We stole it from that.
All right, so, oh, sorry. No, yes, these are just exceptions to normal elements.
Transition.
Ions are up next. No. It's KR. So I'll give you a minute to finish getting this. Do y'all know why we would want to form a cation or an anion? Why would we want to gain electrons or lose electrons?
To get to be a noble gas.
Yes. Everybody wants to be like a noble gas.
Think of it as noble. Noble.
Yes, they're noble. High up.
Yeah.
Because the reason we want to be like noble gases is because they have a completely filled electron. Their outermost electron shell
Perfect.
is completely full. So that is everybody's goal. So your metals, everything on the left side of the periodic table, are going to give up electrons to be like their noble gas. The non-metals, everything on the right side of the periodic table, from where your metalloids separate them, so all of these, they're going to gain electrons to be like the nearest noble gas. Why? It's easier for, say, magnesium to lose 2 electrons versus gaining 1, 2, 3, 4, 5, 6 electrons. Same is true for non-metals. It's easier for them to gain, say we look at sulfur, gain 2 electrons to be like argon instead of losing 1, 2, 3, 4, 5, 6. Okay? So that's why some gain, some lose. So, I mentioned just a second ago, we were talking about these, that elements in the same group have similar properties. They behave similarly. So, we can predict what cation or anion they will form if we're talking about main group metals based on what group they're in. So you might want to label your periodic table with the numbers I'm about to give you.
Okay.
Everything in this group is going to form a +1 cation. So group 1A, +1 cation.
Okay.
Group, I might have it in that packet. Hang on, let's look at this.
So group 2 would be, they would gain 2 cations.
Yes, the very last page of the PowerPoint that I gave you the other day has all of this on it. So everything in the first group, +1. Everything in the second group is +2. I'll talk about these guys in a minute. We jump over here, aluminum will form a +3. Aluminum is the only metal here. Boron, all the way down, those are metalloids. So only aluminum is +3.
Okay.
Then, let's go to the noble gas side. I don't know where I'm going. Noble gases, they're not going to lose or gain. So let's look at the halogens. They're all going to form a -1 cation. So they are going to gain 1 electron. Next row, oxygen, sulfur, etc., -2. Then nitrogen and phosphorus will do -3.
And then carbon.
Carbon's a weird one. Because carbon has 4, is it easier for carbon to gain 4 or lose 4?
It's easier for them to lose 4.
We don't really know. So usually they don't lose any or gain any.
They just,
They
they're
know.
content.
Mm-hmm.
Happy.
They have their own whole chemistry. It's called organic. Okay, so
Interesting.
if you look on that table, you'll notice that there's 2 for most of your transition metals. There are 2 different charges they could possess because they just do whatever the heck they want.
Yeah.
But you don't have to remember all that. If you just remember +1, +2, then on the other side, -1, -2, -3. I will show you a way that we can determine the transition metals charge by looking at a compound, okay? So let's talk about how we write electron configurations for our cations and anions. It's actually quite simple because we're trying to be like a noble gas. So our electron configuration should just be that of a noble gas. So when we talk about this, I'm only referring to my main group elements. So that's everything in the S and P block. Transition metals have their own way of doing it. All right, so let's say sodium. Sodium's normal electron configuration is neon 1s. Oh no, it's not 1, it's 3s. 3s1.
So that's the normal. Okay.
Well, I told you just a second ago the elements in group 1 form a +1 cation. So Na plus, the cation I would form, meaning I've lost an electron. So the electron configuration of the cation is just that of neon. How beautiful.
So neon is just perfect.
Now sodium is. Sodium plus.
Sodium plus. So this is the cation configuration.
I formed a cation by losing an electron, so I lost this 3s1 electron, so now I'm just neon. Alright, let's look at another one. Let's do aluminum. Aluminum's normal electron configuration, not cation, just the element. Neon 3s2, 3p1. What type of cation or what number cation does aluminum like? 3 plus.
3 plus.
So I formed this 3 plus by removing these 3 electrons. So now
I'm neon.
Yep.
Perfect.
Yes.
Okay, I follow you.
The next part. So this plus charge, you can never take away protons, in case y'all missed that on your test. You can never change the number of protons. You can change the number of electrons and neutrons. You change neutrons, you have isotopes. You change electrons, you have ions. So if I have a +3, that means I have to remove 3 electrons. So I'm going to remove the last 3 electrons in that shell of orbitals. So 1 from the P, 2 from the S, so now I'm just neon.
I like
So
these.
basically,
Mm-hmm.
I like trying to be a noble guy.
Yeah, no, it's quite easy. So your cations or your metals. Metals form cations.
Oh no.
Oh, we're not going to transition metals just yet.
Okay.
So remember, metals form cations. Therefore, anytime you form an ion that is a main group element, form a positive ion, the main group element is going to be like the preceding noble gas, the one right before it.
That's what it's trying. That's what it wants to be. Is the one that is right before it.
We're talking about anions.
And it's almost hard to say for some reason.
Too many A's, I's.
Yes.
all that.
Too many vowels.
All right, let's look at
Separated.
anions. Oh, yeah.
So you know how you guys emailed for the ALK plus?
Mm-hmm.
Why don't you have like 2S and then like 2P for the neon space?
Like after it.
Yeah, like for ALK plus equal for the neon space.
Anything after it.
Yeah.
Because we took away those 3 electrons that were in there. So we had the so this is normal aluminum. If I form aluminum 3 plus, I remove these 3 electrons. So that's no longer there. So it's just that. That makes sense? All right, let's do negatives.
So anion.
I don't know if we have this joke on that board out there, but cations are positively charged, like cats have paws. I'll be here always.
All summer.
Yeah, I'll be here all summer. Come to the show. All right, anions. We're gaining electrons to be like the nearest noble gases. Yes, ma'am. Cations are positive. Anions are negative. Negatively charged.
So we're gaining electrons. To be like the nearest.
Yeah, we just did cations. Now we're doing anions.
Even if I said
Negatively charged by gaining electrons.
like the nearest.
Who are you going to do pouring?
I can't ever tell if he's serious or not.
All right, normal chlorine would be neon 3s2 3p5.
I like how you did the normal. Not. 3S. Normal.
So what kind of negative charge does chlorine prefer? -1. So what it does is it adds 1 electron to this last p orbital, so the 3p orbital, and it becomes that of argon.
It's 3.
So this is what your normal,
So it'd be 3S. Wait, 3S to 3P6.
yes ma'am. Yeah. Okay, so this would be my normal electron configuration for chlorine. But when I gain an electron, I'm adding it right here, so it becomes that of R naught. So this one electron makes it just like argon.
So it didn't take away,
It gains.
I mean, it gains.
So no, yeah, we didn't remove. So all
This
your
might be a stupid question, but where to get it from?
somewhere.
Okay.
Usually what happens is the metals lose the electrons and they give them to the anions.
Okay.
And like if you're forming a compound, that's what happens.
I got you.
Yes,
Why is it negative if it's gained?
because it's a negative charged particle.
So
The
it
electron
can,
is negative,
it can gain.
so it becomes negative. Because now you have more electrons than you do protons. All right, so anytime you form an anion, you're looking at the noble gas that follows. So if I formed oxygen 2 minus,
You want to be helium?
you would go to the one after it. Because you're
Okay.
gaining 2.
Okay.
So it'd be neon.
Yeah. So it's like, you're not going the one above like we've been doing.
Right, you're going the one after.
Okay. Okay. And I think did I write that down? We didn't do that with the cations, though, did we?
The cations, we lost electrons.
Right, so we went back up.
Now we're
Now we're
gaining.
just going 2. Getting 2 there. Okay. I need to write that down because
Backwards.
okay, so anions, I gotta write that down.
Anions gain and go forward.
Okay. Well, I did do the nearest noble. I did write it down. Go to the nearest noble gas. So that's what that meant.
Yeah. All right. So your main group metals, they're pretty easy. They're predictable. You know what they're going to do. Now let's talk about those nasty transition metals.
So transition cations and anions.
Yeah, so transition metals are metals, so they're only going to form cations.
Okay, transition metals. I can't read.
Either. Questioning my spelling of transition.
I know you see. They only form anions. Cations. Because they're positive.
Charged.
Are you going to put the slides on?
Yes,
Or
I'll do that.
do we
this
need
afternoon.
them?
You don't need them, but I will put them up for y'all this afternoon.
I just like going back and filling them in.
Yeah.
And then the practice problems.
So the deal with transition metals is because the s orbital is lower in energy than the d orbital, you always take away s electrons before you take away d electrons. So
take away s electrons.
because the s electrons are lower in energy than your d orbital, you remove them first.
Or
So say I was in the 4s orbital, I'd be in the 3d block. There's always one less. Alright, so let's write the electron configuration of iron. Then we'll do its cations. So preceding is argon.
so
4s.
so you go to the preceding one with this one.
Oh yeah,
Yeah.
this.
Yeah.
Yes.
We're doing the normal. We're doing
Yeah,
the normal. I'm sorry.
You're fine. Another thing about transition metals, they don't want to be like the noble gases. So when they lose electrons, they're not becoming a noble gas.
That makes a big difference. God bless you.
Alright, so for iron, there are two different cations it makes form, whatever. So one is the 2+. So to form the 2+, I'm removing 2 electrons. But I'm taking them from the s orbital, not the d orbital. So the configuration becomes
4s.
0, 3d6. So I was only had to remove 2, so I took them from the s orbital.
So,
Go ahead.
so I thought the s orbital was closer to the nucleus. So shouldn't that mean it has a stronger pull toward the nucleus?
Yes, but it's still lower in energy in terms of atomically than the d orbital. And with transition metals, they form like weird complexes, so they prefer to have a lot of open space, basically. So by taking these, I just open up a new orbital for other bonds to be formed.
So you have to write more.
I prefer that you do, just so you can show that they're removed, but you don't have to.
So even though we take the valence electrons from the last orbital,
Right, but we take them because the S is,
consider them outside.
right,
We take the actual electrons from the
S in this case. Another iron likes to form 3+. So go back to the starting point. I want to take 3 electrons this time, so I'm going to take 2 out of the S, and I'm going to take 1 out of the D. So it's 4s0, 3d5.
So where did that electron go? We just know it just takes away.
Yes, and so again, normally, if I'm taking away from a metal, there's a non-metal around
Somewhere
to
that's
accept.
taken up, yeah. Okay. I mean, they just like have them all just shooting everywhere. I mean, they're just
It's just what they do.
all over the place.
They're like feral cats.
I mean, that's It'll be stuck in my head now.
Yes.
Okay, what did you say?
That's great.
2 plus S3 was a component.
That tells me how many electrons I'm removing, taking away. So I'm taking away 2 with iron 2 plus. I take them away from the s orbital. Taking away 3 this time, so I take 2 from the s, 1 from the d.
This is not as bad as I thought.
It's just remembering to remove s electrons
For
first.
this one, this
Yeah, I think that's
Just
usually
practice.
the problem.
It's just gonna practice.
We'll do one more. Let's do manganese. Okay, so I'm gonna go ahead and do I always start by doing the normal electron configuration. That just helps me know what it looks like to begin with.
It's 4s2.
3d5, right? 2, 3, 4, 5, yes.
3, 4, 5.
And so that's my normal electron configuration for manganese. Manganese likes to form a 2+ cation, so it removes 2 electrons. Well, that takes care of both my s electrons, and I don't have to go to the d's to remove anything.
So it's 4s0.